Imagine what it would be like to discover a magnetic material for the very first time and have no idea about what magnetism is. What would you think? Well, early man thought that a rock like lodestone that was magnetic had some magical power in it, some mystical spirits, because it could attract objects to it with some invisible force and have the objects stick to it. He immediately turned to medicine and started using this lodestone to remove evil spirits and sickness from people's bodies. We know better now because we understand magnetism, but it's still a very fascinating subject, especially for young children discovering the ideas of magnetism on their own. And if I think about my own experiences in the primary grades, it was magnetism that got me started as a science person. To do magnetism justice, to teach it properly, you need to have equipment. You have to have magnets, you have to have compasses, and you have to have iron filings to plot these invisible force fields. Let's start by taking a look at some of the equipment you can use. The most versatile type of magnet is a bar magnet, and you should have enough bar magnets so your students can work in small groups of 2 and have at least 1 magnet per group. These magnets come in 2 different types of materials, steel or alnico. And alnico, by the way, is an alloy of aluminum, nickel, and cobalt. Alnico magnets are stronger but cost a little bit more. Another real interesting type of magnet is a ring magnet. Ring magnets are lightweight but very strong and not very expensive. They have the North Pole on one side and the South Pole on the other. And when you stack them on a pencil with all the same poles together, you can see that they're repelling, and you can do a lot of really fascinating little things with them. Third type of magnet is a horseshoe magnet, and they come in many sizes. This is a large horseshoe magnet. You should have at least 1 of these in your school so you can look at the magnetic field lines. Another thing you can do with a large magnet like this is lift heavy objects and show students that magnets can be used to do heavy work. When this horseshoe magnet's not in use, it should be put away with a keeper across the poles. It's a piece of steel. This runs the magnetic field lines through the steel and saves the magnet for future use. And while we're on that subject, when you're putting your bar magnets away, have the north and the south pole of 2 magnets line up and have them connect together. This is the way to store them. It works the same as a keeper. Another type of magnet, but a magnet on a pivot, is a compass. And I like to use the large compasses. This is about 40 millimeters across. Stay away from those tiny ones. They don't work very well. And these are quite inexpensive. You should have enough of these as you have bar magnets because they go together. Finally, iron filings. You can order them from a science supply house. You want to order about £1 for your class. And store the iron filings in an old salt or pepper shaker. But as you do with all your other chemicals, be sure and write on the outside on a piece of tape what's in there. Nothing's worse than putting iron filings on your mashed potatoes. Now that you're well equipped, the first concept that you want to develop is what is a magnet, and how can we determine if an object is a magnet or not? Well, to do this, we need to have a compass. A compass, remember, is a tiny little magnet. And the object we want to test to see if it's a magnet or not, it has to satisfy 2 requirements. The first one is when the object is brought near the compass, one of the needles will point toward the object. When we flip the object around, the other needle now points toward the object. If both of these requirements are met, the object is a magnet. What if just one of them is met, like a paper clip is brought close to a needle of a magnet? Well, because it's metal and because this is a magnet itself, the magnet may be attracted toward the paper clip, but it won't repel or it won't draw the other pole around when you flip it around. That's an important point to bring out. Now, what actually is a magnet? Think of this as thousands of tiny little compasses all pointed in the same direction. If they're pointed in the same direction, we have a magnet. If they're all pointed randomly in different directions, then we don't have a magnet. You can further demonstrate this with a test tube of iron filings. First, test it to see if it fits the 2 requirements. Does one end draw one side of the magnet and does the other draw the opposite? doesn't work if it's just a random order of iron filings. But what happens if they're all lined up, magnetically lined up? Well, you can do this with a very large, strong magnet. Take just one pole and stroke the test tube about 30 times. Stroke it only in one direction. And as you do, turn the test tube. Once this is done, you can test this now to see if you've made a magnet. One of the poles of the magnet should be attracted to the bottom of the test tube. The other pole will be attracted to the top. So it satisfies our two rules. Then ask your students what they think will happen if this little magnet gets disrupted and all the little particles get shaken up. Test it again with your compass. Now you'll find that it's lost its magnetism. This is an important concept to develop as students learn proper care of magnets. Things to avoid, like heating it up, or dropping it, or hitting it with a hard object. Now the next thing we want to look at, and if you have the paper clips and the magnets, do this as an experiment. Where is the most powerful parts of the magnet? Is it the center, the ends? What would it look like? Well, very simply, drop the magnet into a pile of paper clips and pick it up. It's apparent that the forces are on the ends of the magnet and there's very little force in the middle. While you're at it, have your students take the paper clips off and test each pole to see which one is the strongest. How many paper clips can we hang from the North Pole? And how many can we hang from the South Pole? This is a relative indication of the strength of the pole. This one holds 3 paper clips. Now we want to investigate materials. Which materials are magnetic and which are non-magnetic? Now what does this mean? And we also want to see what materials will magnetic field lines pass through and what materials will short them out. Before the students test the materials to see if they're magnetic or not, they should first make predictions. Will a particular material be attracted to a magnet? And list all the objects that they'll be testing. And then let them go around and test the individual objects with their magnet. I've got everything from sesame seeds to aluminum foil pieces to thumbtacks to paper clips, even copper pennies. There's 2 major conclusions that your students should find by doing this experiment. First, only metal objects are attracted to a magnet. And second, not all metal objects are attracted. Now we want to go on and investigate different materials. Do the magnetic force lines go through some materials and not others? How about cardboard? Well, here's how we'll test this. With a paper clip on top of the cardboard, can we move the paper clip along? So it appears to go through the cardboard. What about steel? Let's try it on the steel. In this case, it doesn't move the paper clip. So the steel must be shorting out the magnetic field. You can try it with glass by dropping it in a Pyrex dish that's sitting on a couple blocks, and you can move the paper clip around inside the glass. What about water? Will these field lines pass through water? We can test that with a cork with a thumbtack stuck in the bottom. We can float it in water in our Pyrex dish, and we can move the cork around with our magnet. This next experiment requires some thought. Ask your students a question. Here's a sample, sample number 1. How can we determine if it's a magnet? How will we find this out? Let the students ponder it for a while. Hopefully someone will come up with use the compass and see what happens when you flip it around. Will the needle spin around on the compass? Remember those 2 rules. And then have them go around with their compasses this time and record whether particular samples are magnets or not. Now, to make these samples magnetic, get your bar magnet and rub one end, and this is a big darning needle, rub it along the North Pole for about 30 times. Then flip the magnet around and the needle around and do the same thing with the South Pole. You'll end up making a fairly strong magnet out of this. Now, we never talked about what happens when poles come together, 2 south poles or a north and a south pole. But this is the place to go next, is look at how these fields repel and these fields attract. And then we'll look at magnetic field lines. Up until this point, we've been treating the compass as just an object that detects a magnet. We haven't said anything about this huge magnet that's in the center of the Earth. How do we develop this idea? Well, remember, your students have to have a good understanding of north and south poles attracting and north poles repelling. Give them time to develop these ideas first. And then ask them to bring their compass out and a north pole of a magnet and see and record which part of the needle on the compass is a north pole and which part is a south pole. And then ask them, if we put this compass all by itself away from all other magnets, it always tends to point one way, no matter how much we turn it. What does this suggest? Hopefully someone will say, well, there must be some huge magnet up there that's pulling on it. And what pole must that magnet be? If we've decided using our north and south pole that this is a north magnetic pole, a north end of a magnet, and it's pointing that way, then we must have a huge south end of a magnet up there somewhere, the magnetic field of the Earth. And then ask them this question. If we get two magnets and we tape up the poles so you can't see which is which, can we tell which one of these is a north and which is a south? The real answer is you can't really tell which is north and south, but you can tell which ones are alike and which ones are different, depending on whether they attract or repel. If you could set this in a cradle and let it spin freely from a thread, you could tell, because the north pole would tend to point north. Now, while we're talking about compasses, there's some really interesting homemade compasses you can make. This one uses a piece of cardboard with our magnetized darning needle run through it, and you can balance it by moving the darning needle back and forth. The cardboard's connected to a piece of thread which is tied to a pencil, and it's hanging in a jar for support. Next we have the floating compass. This time I've taken a magnetized darning needle and taped it onto a cork. When I set it in water, it spins around and lines up with the Earth's poles. What about these invisible field lines? We can't detect them with our senses, but we can detect them with iron filings. An easy way to do this is to use your overhead projector, set the magnet on it, and then a clear glass dish, and then sprinkle the iron filings in the dish to project the image. Another way that all the students can get involved with is using that light-sensitive paper. It's called solar graphic paper or sunprint paper. And have the students tape it onto a piece of cardboard. Keep it covered till they're ready to use it. Take it outside and set it over the magnet, and then take about a minute to sprinkle the iron filings on. And then let it sit in the sun for an additional 5 minutes or so before you develop it in water. You get some very exciting results. This is what I got when I tried a bar magnet. And this is what my horseshoe magnet looks like. And then I wanted to get a close-up of the two poles of the horseshoe magnet, so I did a wide shot of those and got this pattern. Now, if you can't find this paper, there's another way to do it. Set up your iron filings under your magnet on a piece of cardboard and then hit it with some spray adhesive. Do it outside to avoid vapors. You can make some very nice patterns like this. Either one of these could be used in a real nice bulletin board display with the actual picture of the magnet underneath it. Now we want to use the same technique and investigate how different fields interact. This is what we get when we have two of the same fields coming together. They push apart. And this is what it looks like when opposite poles attract. Now, many people know that magnetism and electricity are closely associated, but they don't really see the link between the two. This next activity will be a very good transitional activity from magnetism to electricity. Before we develop this relationship between magnetism and electricity, let's first see what electricity is all about. Think of it as flowing water, a moat around a castle. And the king wants to turn his moat into a playground. He wants his friends to come and sit in boats and get free rides all the way around the castle. So he wants some kind of source, something to push the water, make it go around in a circle. What could he use? Let your students think about that one. Every one of the solutions should require some type of power source, something to drive or push on the water to push it around in a circle. Whenever we have an electric circuit, we must also have a complete circle and some kind of driving source, electricity. And not pushing water this time, but pushing tiny particles called electrons through the wire. And the electrons always flow from minus to plus. Now, let's say this king got his little system going with all his water rushing around, and a villain comes by and throws all these boulders into his moat to stop the water. What'll happen to the water? It'll start to slow down. There's now boulders in there offering resistance, pushing back against the water. And when we think of a light bulb, this is a good analogy for resistance. This light bulb slows down the flow of electrons and turns much of the electrical energy into heat and light that we can use. Now we want to set up a complete circuit. Your student should understand how to do this. Here's the pieces of equipment I'm using. A 1.5 volt D cell, and it's in a battery holder with wires coming out of it. I'm using a very small light bulb with screw threads. This is a 2.5 volt bulb, and it has a socket that it'll screw into. The socket has little tabs, and we can connect wires onto the tabs to make for easy connections. The first thing we want to demonstrate is a complete circuit. We'll get the light source, which is our resistance, and our battery supply, and make a complete circle all the way around. The light bulb lights up. If the circuit's broken anywhere along, then the light bulb will go out. You can further illustrate this by having all of your students stand around and hold hands. One person squeezes the next person's hand. When he or she feels it, she passes it on. Now, if the line breaks anywhere in the circle, the pulse stops. And you may find a kid before you do this and tell him the third time around not to squeeze the hand when he feels it, and have the rest of the students try and track down where the break in the circuit is. This is exactly what we do when we're troubleshooting an electrical circuit. Students can go on and test different materials by making one of these connections a permanent connection and leaving the other two open, and testing things like paper clips to see if they conduct electricity or not, and sesame seeds and pieces of wood, all the things we tested when we tested the magnets, recorded once again on a lab sheet. Now we want to get to this relationship between magnetism and electricity. There's something there, and it has to do with this copper wire, this coil of wire. Is it a magnet right now? Well, we can test it with our compass. What happens to it when we connect it up to our power source and we start running electricity through it? Well, once it's connected up, when we bring our compass near it, we see that it's now a magnet. When electrons flow through wire, they make a magnet. And you can even further illustrate this by wrapping about 6 turns, this is 18 gauge hookup wire, around a compass. It can be just about any kind of wire and work. When you touch the contact and make intermittent circuits with your battery, 1.5 volt, it makes the needle spin wildly around. Now, to further illustrate this idea, we can go on and make simple electromagnets, and your students will have a lot of fun with these, picking up things, seeing that when the circuit is complete, it'll hold a paper clip, but when they break the circuit, the paper clip will fall. It's important that they understand this relationship, and to do so, they have to have this simple equipment to work with. If your intermediate teacher doesn't have it for you to borrow, your school should invest in simple things like these battery holders. They're readily available at radio parts houses. Electricity, like magnetism, is a very fascinating topic, and any students that are really interested should be encouraged to study it further. Remember that if they're going to do other experiments, only allow them to use batteries like we have here. Advise them about the dangers of using high voltages. And have your students get an appreciation for electricity and all the electrical appliances that help us to do work and do things for us. Have them list the number of appliances they come in contact with in just one day. I'm sure they'll be surprised. It's important that students understand that electricity costs money, and it should be conserved. Where do we go from here? Well, first you can take a look at the intermediate tapes and see how your ideas are expanded upon. And then for continued professional growth, I highly encourage each of you to become a member of the National Science Teachers Association. This is a group of teachers just like you that share ideas and activities in science education. And there's an excellent publication you'll receive entitled Science and Children. It's packed with new ideas and developments in science education. Remember, the success or failure of science depends on each of us doing our part.